Data transmission line propagation delay is the duration of time that the data signal takes to propagate from one point in the transmission line to another. It is the reciprocal of propagation speed. Any transmission line can be characterized by transmission line parameters such as resistance, shunt conductance, inductance, and capacitance. The characteristic impedance can be given by the equation. Speed of signal propagation is affected by the characteristic impedance and is given by Z0 equals square root from inductive impedance divided by capacitive conductance. The speed of signal propagation is affected by the characteristic impedance and is given by frequency equals 1 divided by square root from inductance times capacitance. In engineering, ideal conditions are usually confined to case studies. Real-time engineering systems deviate from ideal conditions, and corresponding changes can be seen in output characteristics. In the case of data transmission lines, the resistance, shunt conductance, inductance, and capacitance are the line parameters causing non-idealities. The non-idealities in transmission lines majorly affect reliability and signal integrity. One such concern, called transmission line propagation delay, is a phenomenon due to the inductance and capacitance present in the transmission line. This delay can cause serious problems for the signal integrity of a system. Data transmission line propagation delay. Data transmission line propagation delay is the duration of time that a data signal takes to propagate from one point in a transmission line to another. It is the reciprocal of propagation speed. The propagation delay is related to inductance and capacitance per unit length of the transmission line. The transmission line propagation delay per unit length can be given by the following equation, where TPD is the transmission line propagation delay, L0 is the characteristic inductance per unit length of the data transmission line, and C0 is the characteristic capacitance per unit length of the data transmission line. Propagation delay. The propagation delay, TPD equals O times CO, is the time delay through the transmission line per unit length. It depends on the characteristic impedance and characteristic capacitance of the bus. Figure 3. Effective propagation delay for a loaded bus. You can calculate the effective propagation delay with this equation. You can calculate the time for the signal to propagate from driver A to receiver B as the TPD-EFF times length of line between driver A and receiver B. Effective impedance. The effective impedance depends on the bus trace characteristic impedance ZO and capacitive loading on the bus. The connectors, the stub on the plug-in card, the packaging, and the receiver input capacitance all contribute to capacitive loading, which reduces the bus effective impedance. Equation 1. Effective differential impedance equation. Use this equation to approximate the effective differential impedance of the loaded bus, ZEF. The increment in load capacitance or closer spacing between the plug-in cards reduces the effective impedance. To optimize the system performance, it is important to select a low capacitance transceiver and connector. Keep each receiver stub length between the connector and transceiver I/O pin as short as possible. Where Z-diff, 2 times ZO equal the differential characteristic impedance of the bus. Co, PF/inch, equal characteristic capacitance per unit length of the bus. Class, PF, equal capacitance of each load. N equal number of loads on the bus. H, inch, equal D times N equal total length of the bus. D, inch, equal spacing between each plug-in card. CD, PF/inch, equal class/D equal distributed capacitance per unit length across the bus. The influence of dielectric material on transmission line propagation delay. The signals transmitted through the transmission line are electromagnetic, and electromagnetic signals travel at the speed of light in vacuum or free space. The data transmission line is made of 2 or more conductors of some length, separated by dielectric material. The propagation of the signal through the line creates an electric field between the conductors, and the current flowing through it produces a magnetic field. When the electromagnetic signals propagate through the transmission line, the dielectric material surrounding the line decreases the speed at which the signals are transmitted through it. If the transmission line is surrounded by free space, the speed of propagation is equal to the speed of light, c, which is 3x108 m/s. In data transmission lines, the dielectric material property influences the propagation delay and is proportional to the relative permittivity or dielectric constant, ER, of the material. It is a number that gives the measure of the material's ability to propagate the electric field compared to vacuum. The dielectric constant of vacuum is unity. The propagation delay can be given by the equation. Consider the transmission line propagation delay when designing a system. When designing communication systems, the transmission line propagation delay should be considered a design parameter. As the propagation delay is dependent on the characteristic impedance, designers must make sure the impedance is constant throughout the line and the LC product is minimized to reduce the propagation delay, ensuring signal integrity of the system. It is important to note that dielectric material is not a perfect insulator and leakage current flows through it. Moreover, the transmission line will be always under the influence of the electric and magnetic fields, due to the presence of voltage and currents, respectively.